All right, next up, let's take a look at what is called delta G, or change in Gibbs free energy. Don't worry too much about what free energy is. Basically, what we're going to do here is we will use the sign for delta G for a reaction to determine if a process occurs spontaneously or not. So as we'll see in a little bit, delta G combines values of delta H and delta S, the two factors, or I should say two of the three, as we'll see in a minute. Factors that determine if a process will occur all by itself or not. So there's actually, like everything else we've seen so far, a couple different ways of calculating delta G. So the first one involves using delta H and delta S. So here is that equation. And technically these are delta G naughts. And so we see delta G naught equals delta H naught minus T delta S, where T is the third factor that affects the spontaneity of a process. Not always, but we'll see that sometimes temperature affects spontaneity. So T is the temperature in Kelvin. Again, if we're talking about reactions that occur at standard conditions, this would be 298 Kelvin. For this class, I don't know, we may do some situations where the temperature is not 298 Kelvin, but I think for the most part we will do 298 Kelvin. I sort of alluded to this yesterday, so be careful. Be careful of the units. Delta G is often measured in kilojoules per mole. Delta H is in kilojoules per mole. But delta S is in joules per mole Kelvin. And so what we're going to see is that when we plug in a value for delta S into the equation to solve for delta G, we need to take that value and convert it to kilojoules per mole Kelvin. Back here, the book, though, gives it in joules per mole Kelvin, so just be careful with that. All right, so let's take a look at an example. Probably could have predicted what we're doing here. Calculate the delta G for the combustion of 1 mole of methane gas. And it says to use the values that we already calculated for delta H for this reaction and delta S. So remember, this reaction occurs at 298 Kelvin, so that's the temperature that we're using. And I think I'm going to let you go ahead and solve this on your own. So go ahead and pause the video and see what you get. All right, so we calculated delta H for the combustion of 1 mole of methane earlier in the notes, negative 803 kilojoules per mole, minus T delta S, where our delta S, was negative. I may have done this wrong. Let me pause and make sure I got the right numbers here. Hold on one sec. Sorry, this is negative there. I didn't have a negative at first. So minus T delta S. So minus a minus is going to end up being a plus. So negative 803 plus about 1.4 something, I think it is there. And we end up with a value for delta G of negative 801 kilojoules per mole. All right, we will talk about the significance of the sign of delta G in just a bit. Just know that for this reaction, delta G is negative. All right, so the other way to calculate delta G is kind of like what we did with delta H and delta S, where we are going to use the delta G of formations of each of the substances involved in the reaction, delta GFs. And so like always, we're going to do the sum of the delta GFs of the products. And I didn't write delta GF, but that's what it is. Minus the sum of the delta GFs. That's a kind of weird sigma there. Sorry about that. Delta GF of the reactants. So again, you may have noticed in the table of thermodynamic data, you have delta HFs, delta GFs, and again, those are both for formation reactions, and then absolute entropies, or S's. And so products minus reactants will give us delta G for the reaction. All right, take a look at number 14 on page 702. And what we want to do is calculate delta G for that reaction. Go ahead and pause the video and set that up and see what you get. All right, so here's the values I used from the back of the book. Again, just use all the significant figures. And so we want to estimate to the 1 digit after the decimal. And I rounded those values, so you may have gotten some a little different if you did it all in one shot. So I get negative 57.0 kilojoules per mole. So now what does this mean exactly? I mentioned earlier that we can use a sign for delta G to determine if a reaction is spontaneous or not. So here's how it works. If delta G is negative, that means the reaction will occur all by itself, meaning spontaneous. A word that we use for this is exergonic. I usually don't use that term. A College Board will use a term thermodynamically favored. Again, meaning that this reaction will occur all by itself. Conversely, if delta G is negative, that means the process is non-spontaneous, or it is not thermodynamically favored and will not occur by itself. What if it's neither positive nor negative, but rather zero? If delta G is zero, that means both the forward and reverse reactions are spontaneous. And so when is that the case, where both the forward and reverse reactions are spontaneous, where both reactants and products are favored? That would be at equilibrium. And so probably not going to see that. It's usually delta G is either positive or negative. So those two examples we did, both reactions, the combustion of methane and then this one here, number 14, are both spontaneous at 298 Kelvin. All right, so let's make a table. And in fact, I'm going to add something to this table. So let's do that now. Let's add delta G to this table. So what we're going to do is we're going to look at these signs for delta H and delta S and see how that affects the sign for delta G, and then make a statement about whether or not this kind of process is spontaneous. So let's start with the processes that are favored in nature. In terms of energy, what kind of processes are favored in nature? Endothermic or exothermic? That would be exothermic. So let's say we have a process where delta H is negative. In terms of entropy, what is favored in nature? Processes where entropy increases or entropy decreases. That would be increases. And in that case, then that means delta S is positive. So let's take a look at the equation for delta G, and let's just plug in some hypothetical numbers here. So let's say delta H is negative 100 and T delta S is positive 50. Using those numbers, what would be the sign for delta G? Well, it would be negative. Notice that T delta S right now is smaller than delta H. What if it was bigger? Let's make it positive 150. Now remember, temperature is always positive. There's no negative Kelvin temperatures. So whatever the sign for delta S is, will be the sign for T delta S. So in this case, if delta S, T delta S rather, is bigger than delta H, then that means delta G is still negative. Now, what affects the magnitude of T delta S? It's actually T, the temperature. So what we're saying in this situation is it doesn't matter what the temperature is, whether the magnitude of T delta S is bigger or smaller than delta H, doesn't matter. Delta G will be negative. And so what we say that this process is always spontaneous, meaning no matter what temperature this reaction occurs at, it will occur all by itself. All right, let's go the other way around. Let's look at the processes that are not favored in nature. So in terms of delta H, we're talking about endothermic processes, so delta H positive, and a process that decreases in entropy, delta S is negative. So again, let's look at some numbers. So let's say that is, I don't know, we'll go with positive 100 and negative 50. If we use those numbers, what is the sign for delta G? Well, minus a minus is a plus, so we get positive. What if T delta S is bigger than delta H? Well, we still get positive for delta G. So an endothermic reaction that's, decreases in entropy, the sign for delta G will be positive, which means what? One of two things, either always non-spontaneous, or better yet, never spontaneous. Meaning no matter what temperature this reaction occurs at, it will not occur by itself. All right, so we have a total of four to look at. So we got 2 so far. So let's look at another situation. What about an exothermic process, favored in nature, that decreases in entropy, not favored in nature? So again, let's use some numbers here. So let's go with negative 100 and negative 50. So using those numbers, what is the sign for delta G? Delta G will be negative. Well, what if T delta S is bigger than delta H? Now what is the sign for delta G? Well, now it's positive. So what does that mean then? We have an exothermic process that decreases in entropy. What is the sign for delta G? We don't know. It depends. Well, what does it depend on? It depends on the temperature. So how can we make this so that delta G is negative? That's only when T delta S is smaller than delta H. When would T delta S be smaller than delta H? Well, think about what I said earlier about the magnitude of T delta S. It is determined by temperature. And so what we say in this situation is that this process is sometimes spontaneous. And what ultimately will determine the spontaneity of this process is the temperature. And this kind of process will only be spontaneous at some lower temperature. I don't want to get into the details about what temperature, but just some lower temperature. All right, let me give you an example of this. Let's use the example of freezing of water. First of all, that process is exothermic. Freezing is exothermic. And freezing involves changing from a liquid to a solid, so that involves a decrease in entropy. So we got delta H negative, delta S negative. Question, does water freeze all by itself? Go ahead and pause and think about that. If you said yes, water freezes all by itself, I'll argue with that. If you have water sitting out in a cup on the counter, it's going to turn into ice all by itself? I don't think so. If you said no, the process is not spontaneous, then I'll say, okay, well, you take some water, put it in the freezer, it doesn't turn into ice all by itself? Yes, it does. So this process, the freezing of water, is the spontaneity depends on temperature. Water will freeze all by itself at what temperature? Any temperature below 0 degrees Celsius. Anything above 0 degrees Celsius, water will not freeze all by itself. So that is an example of a process that is temperature dependent. All right, we have one more. Can you guess what it is? Endothermic process, not favored in nature. Increasing in entropy is favored in nature. So let's go with positive 100 and positive 50. Using these values, what is the sign for delta G? Well, delta G is positive. What if T delta S is bigger than delta H? In this case, then, delta G will be negative. So, once again, we don't know the sign for delta G. We know that this process is temperature dependent. So once again, we'll say sometimes spontaneous. And at what conditions will it occur spontaneously? Some relatively high temperature. All right, so what's an example of this? Let's go with melting of ice. Question, does ice melt all by itself? Go ahead and answer that. If you said yes, I'm going to argue with that. Ice in your freezer turns into liquid water all by itself? I don't think so. If you said no, I'm going to argue with that. No, ice does not freeze all by or does not melt all by itself. Okay, if you have ice sitting out on the counter, it won't turn into liquid water all by itself. Yes, it will. So when does this process occur all by itself? At any temperature higher than 0 degrees Celsius. If you have ice at a temperature of greater than 0 degrees Celsius, it will all by itself turn into a liquid. So again, just a reminder, melting is endothermic, delta H positive. Melting involves changing from a solid to a liquid, so that involves an increase in entropy. In your book is a similar table to the one we just produced here. So go ahead and take a look there. And then let's do some more practice. Go ahead and go to 702, do practice problem 15. It says calculate delta S for the following reaction. Use the table in the back of the book as necessary. Figure out which way to calculate delta S depending on what information you have, and then go ahead and do that. Everything you need should be in the back of the book. Go ahead and pause and do that now. So I believe you have all of the values for absolute entropy, so we can do products minus reactants. And in doing so, we get 32.9 joules per mole Kelvin. All right, number 16 says computes the Gibbs free energy change, so delta G, for the following reaction. And then based on that value, determine if the reaction is spontaneous or not. So take the equation as written, calculate delta G. Go ahead and pause and do that now. All right, delta GFs of the products minus delta GFs of the reactants. And so we take 2 times the delta GF for HF, and we get negative 546.4 kilojoules per mole. I just went ahead and rounded there to 3 sig figs. And so notice delta G is negative. Actually, no, sorry, that is not negative. It is positive. Sorry about that. Delta G is positive. And so that means this process is not spontaneous. All right, one more, number 17. I'm not going to read that out for you, but the information you need is given to you. Go ahead and pause the video and do that one. All right, so this time again, I rounded to 3 sig figs here. The value we get for delta S is negative 130 joules per mole Kelvin. All right, that concludes this lesson. Actually, that concludes this unit. Thank you so much for watching.